welcome to all of you. I am Dr. Parul Yadav, Assistant Professor at the Department of Computer Science and Engineering in Institute of Engineering and Technology. Today's lecture is on code optimization and DAG representation. This lecture covers the topics as follows. First is code optimization. Under code optimization criteria and principal sources of optimization. Then loop optimization. Under loop optimization, basic blocks, flow graphs, then the techniques of code optimizations like code motion, inductive variables and strength in reduction. Then we will discuss DAG representations of basic blocks. Here DAG construction and one simple example where we will draw the DAG for given 3 address code. Now first is the code optimization. So a compiler generates the target code for the source program. So input to the compiler is source program, and source program is actually the specification of computation, and compiler produce the output program. That output program is actually the another representation of same computation. So source program is a specification and object program is another specification, but of the same computation. Now for each source program there are infinitely many object programs, infinite mean more than once here I want to say, that implements the same computation. So for same computation many object programs can be there. Some of these object programs may be better than the others with respect to some criteria like size and space. So code optimization, the term code optimization refers to the techniques that a compiler employs to produce a better object program. So we need to generate an optimized, we need to generate a better target code in terms of its space and the time required. Now there are certain criteria for code optimizations, mean the 3 criteria are there. First is, does the optimization capture most of the potential improvement without an unreasonable amount of efforts either by compiler implementer or by the compiler itself. So it should this effort should be optimized. Now does the optimizer preserves the meaning of the source program? This is again very important criteria, that the meaning should be same. Next is, does the optimization at least on average reduce the time or space taken by the object program? So meaning should not change, it should capture the potential improvement, meaning should not change, and it should reduce the space and time required by the object program in comparison to the source program. Now there are certain principal sources of optimization. Actually optimization is performed after the syntax analysis. So usually it is done at both the stages, before or during the code generation. So how to do the code optimization? First we detect the patterns in the program, then replace these patterns by its equivalent and more efficient constructs. So there are the techniques using which will change or replace the patterns with the efficient versions of it. Now second is, the patterns can be found locally or globally, and replacements can be machine dependent or machine independent, mean architecture dependent or architecture independent. Now next is the richest source of optimization is efficient utilization of registers, mean registers should be efficiently utilized, and second is efficient utilization of instruction set of machines. So this is the richest source of optimization. Now apart from this, another most important part is the inner loop. The program that we are designing may be having certain loops, that are the inner loop part, and this is most heavily traversed part of the program, and this is a major target of optimization. and we have a rule that is 90-10 rule. It says that 90% of time is spent in 10% of code, mean if a programmer has designed a smaller code, mean line of codes are less. So, this is generally found that in optimization generally it takes a lot more time. So, in loop optimization, one idea is that we remove the loop invariant computations, mean there are certain computations that can be kept outside the loop. So, that type of computations can be removed from the inner loop section. Now, there are three interleaved areas where we do the optimization. One is a local optimization, second is loop optimization, and third is the data flow analysis. Now, we will take one example to understand about the code optimization techniques and the basics related to designing blocks, finding the leaders and doing the data flow analysis. So, first suppose we have this program where this is beginning, then one variable product is equal to 0, I is equal to 1, then do, and in this begin product is equal to product plus ai into bi, if you mean there are two arrays and two indexes, values at two indexes need to be multiplied, and this will be added to product, and then again it will be assigned to product variable. And in every in this loop I is updated, I is equal to I plus 1, this is and loop is for I is equal to less than or equal to 20. It mean this index will vary, will range from 1 to 20, mean 21 times it will be executed, and this is end. Now, we can write the 3 address code for this source program. 3 address code we already know. In 3 address code, result of every computation will be stored in some temporary variable, and in particular statement in 3 address code, other than assignment operator, at most one operator may appear. Now, we can write the 3 address code for this given program. First is beginning, then in after this product is equal to 0. So, we can write product is equal to 0, then I is equal to 1. So, I is equal to 1, and here the word size is 4. So, we can write T1 is equal to 4 into I, and then T2 is equal to address of A minus 4, and this is basically related to A, and this is the index, that is T1. So, what we can do, we can take another variable T3, and T3 is equal to T1 at T2 at T1. Similarly, we can calculate a T4 with respect to array B, and then at array B and for index Ti, this value can be stored in T5. So, this is in T3 and this value is in T5 temporary variable in intermediate code representation. Now, these two needs to be multiplied. So, this is T3 and this is T5, they will be multiplied, and result of this temporary computation is in temporary intermediate computation is in temporary variable, that is T6. Now, product is equal to product plus this value. So, product is equal to product plus T6. Now, I can also be updated, I is equal to I plus 1, I is equal to I plus 1, and then we have while I is less than or equal to 20. So, if condition, if I is less than or equal to 20, will go to step 3. So, this is a step 3, right. So, this is the intermediate code for given program. Some of the optimizations have already been performed while writing this 3 address code. For example, here we have written I is equal to I plus 1. This would have been written like I plus 1. It should be stored in some temporary variable, and this should be assigned to T. This T should be assigned to I. So, but we have performed certain optimizations while obtaining this 3 address code. So, in short, we have obtained the 3 address code for the given program. Now, next step is to find the basic blocks. Basic blocks mean just to break down the sequence of statements in 3 address code into certain blocks. So, the idea is sequence of consecutive statements which may be entered only at the beginning, and when entered are executed in sequence without halt or possibility of branch. So, they will be kept in one block. So, break the sequence of 3 address code into basic block. So, first we will see how to get the basic block. So, idea is in basic block there will be input, output and some method to get the basic block. So, in input this is the sequence of 3 address code statements. So, whole intermediate representation will be input, intermediate representation in 3 address code will be input to it. Output is a list of basic blocks with each 3 address statement in exactly one block. Now, method is first we will determine the set of leaders in 3 address code we will obtain the set of leaders and then we will construct basic block for each leader. So, first step in method, first step is to get the leader and then to construct the basic block for each leader. So, how to get the leader? So, there are three steps or 3 ways for getting the leader, 3 steps. First statement is the leader. So, we will write the 3 address code, this is the 3 address code. So, first statement of every code will be the leader. So, statement 1 this will be treated as leader. Now, second is target statement of the conditional or unconditional go to is a leader. Now, we will look at here, we will find is there any conditional statement. Yes, here we have this go to statement and it is targeting to statement 3. So, statement 3 will be the leader, right. So, it will be the leader. Next is statement that immediately follows a condition. Go to is a leader, means here we have the go to statement, a statement just after it, suppose we have the 12th statement. So, this can be the next leader, but this is end of the program. So, here in this representation we have only 2 leaders, statement 1 and statement 3. Now, next is after getting the leaders we can construct the basic blocks. So, construct basic block for each leader, it means here we have 2 leaders. So, definitely there will be 2 blocks. So, how to construct the basic block? Basic block consists of the leader, it will have the leader and all the statements up to but not including the next leader or the end of the program. So, what we will do? Here we will see what could be the block. So, this is product 1 mean first statement, this is the leader. So, here we can get the first block and in this block how many elements will be there till we are getting this second leader. So, this will be considered as first block. Now, second block can be obtained from here till up to here, right, and then this is actually the end of the program. So, here we are getting the 2 blocks, one is this one and second one this one. Every block will start with a leader. Now, next is for doing the data flow analysis, we will draw the flow graph. So, it is used to portray the basic blocks and their successor relationship by a directed graph. So, it is just like we will have the nodes and nodes will be connected through the transitions. So, here we will be drawing a directed graph in between the nodes. Nodes mean the basic blocks. So, here we will have the nodes, nodes are nothing but the blocks that we have, blocks will be treated as the nodes and will mark the transitions in between that. So, initial every direct flow graph will have a initial state. So, the initial state is the block that carries the first statement of the program. So, this is the initial state. Now, here this is the predecessor and this is the successor, this is a relationship in between the graphs and here we have this loop. Loop will be strongly connected and have the unique entry. So, this is the loop and this is could be the end of the program or could be maybe going to the another block. Now, we will discuss about the techniques like code motion. So, to improve the running time of the program, by decreasing the length of code of its loops. So, place loop invariant computation outside the loop. So, code motion mean inside the loop there could be certain statements that can be kept outside the loop. So, we will move that code outside the loop. So, first we will find the instructions that can be moved, mean we will look at the loop invariant computations. So, here we see that product 1 and I1 this is okay, and here we will have in B2 there is a loop. So, here we will look at, so T1 is equal to 4 into I and I is updated in every iteration. So, this needs to be kept in the loop. Now, this is T2 is equal to address of A minus 4 and then this is used over here T2, then T4 is equal to address of B minus 4 and then it is used here, and after that no use of there. So, these are the two statements that are static in nature, mean they can be moved outside the loop. So, this is B1, this is B2, will create another block that is B3 and these two statements will be kept outside the loop. So, first we will execute B1, then B2 and then this loop section. So, this is about the code motion. Next is the inductive variable, decrease the total number of instructions and speeding up the loop. So, here we can see that here T1 is equal to 4 into I and I is equal to I plus 1, right. So, this is I that is increasing in this loop and then this I will be multiplied by 4 and T1 will be updated. So, inductive variable mean will try to eliminate I from here. So, idea is that here we can write T1 is equal to 0, T1 is equal to 0 and T1 is equal to T1 plus 4 and then this loop can be written from T1 is equal to less than or is equal to 76. Here we have I is equal to less than or equal to 20 because it is started from 1. Now, we are starting from 0. So, it can be executed up to less than or is equal to 76. So, here what we are doing here multiplying I by 4, right, and here we are adding 4 in T1. So, it meaning will same of this computation. So, we can place this we can initialize T1 outside the block. So, we can create a new block that is B4 and then in this B4 we can initialize T1 by 1 and then here we will do the change like T1 is equal to T1 plus 4 and here T1 is less than or is equal to 76 and then we will go to block B2. We will go to block B2 again. So, in that way we can deal with inductive variable. Next is reduction in the strength. This is another important criteria or this is another important code optimization technique where we reduce the costly operator where we replace the costly operator with the cheaper one. So, there are certain operators like multiplication or division, we treat them as costly or expensive operators in terms of their computation. So, they can be reduced using the cheaper operator that requires lesser computation. So, we can see here that here we are doing the multiplication and the step of inductive variable only we change it with the plus operator. So, this is costly operator and this is cheaper operator, mean computational cost for doing the addition is lesser than the computational cost required to do the multiplication. So, this is the change that with this multiplication has been reduced by plus operator without changing the meaning of the computation, and this is called as strength in reduction. So, here this is about the optimization techniques where we reduce the size of the target code. Now, next is a DAG representation. DAG stands for directed acyclic graph. So, this is the graph with no cycles, where no cycles will be there. It gives picture of how value computed by each statement in basic block is used in subsequent statements in a block. So, there can be the computation that is used in the block. So, it shows how it is computed by the statements and are used by the subsequent statements. Now, it determines the common sub expressions within the block. Now, determining the names that are used inside the block, but evaluated outside the block. Similarly, it is used for determining which statement of the block could have their values used outside the blocks. So, this is about the DAG representation, and for computation DAG, a computation DAG is a DAG with the following labels on the nodes. It is just like a tree type of structure that will have the leaves, interior nodes, and one property actually. So, here the leaves that we will have, they will be labeled by a unique identifier. Each variable name and either variable name or constants. So, leaves will be labeled by unique identifier and interior nodes will be labeled by the operator symbols, and nodes that are also optionally given an extra set of identifier for labels. Mean in the interior nodes or at the nodes we can attach some additional information or some extra set of identifier can be for labels, they can be added at the nodes, and this is optional. So, here we will see one example for drawing the DAG for 3 address code. Now, suppose this is the 3 address code, intermediate representation written in 3 address code. So, this is S1 is equal to 4 into I, S2 is equal to address of A minus 4, S3 is equal to S2 at S1, S4 is equal to 4 into I, again 4 into I is computed, then S6 is equal to address of B minus 4, this 4 is reused, then S6 is equal to this S5 at index S4. Now, S7 is equal to S3 and S6 mean the multiplication of these two. Now, S8 is equal to product plus this S7, and then product is equal to this result is assigned back to product, and then S9 is equal to I plus 1, and then I is equal to S8. This is nothing but I is equal to I plus 1, but done in 2 steps, like the first intermediate result is stored in temporary variable and that value is assigned to I. Now, this is the loop for I is less than or is equal to 20 will go to this particular statement 1. So, this is the one block that we have drawn, we have written, and we can draw its DAG representation. So, here first of all we will find out what are the constants, what are the identifiers used in computation. They will be initially at leaf node. So, first we will look at the statement 1 where we have 4 and I, 4 and I. So, here we will have 4 and this is I, right, 4 and I, 1 I. Now, this will be multiplied. So, at leaf part we will have the variables or the constants like 4 into I, and here the interior node will have the operator, that is multiplication operator, and we know that the nodes can be associated with some additional information. So, this is the S1, this value is stored in S1. So, here only we can write the S1. So, this multiplication result is in S1. Now, next is address of A. So, here we will have a leaf node with marked with address of A and minus 4. So, we can reuse this 4 and they will be multiplied, and here we will subtract address of A minus 4. So, this is the operator and then this is assigned to S2. So, similarly here we can write S2. So, this is about the DAG representation for these two statements. Now, next suppose further we have S2 at S1. So, S2 is this one and S1 is this one. So, we can use this operator, that is equal an array. So, this is S2 and here we have index for this is S1, and then this is this one, and S3 mean this will be assigned to S3 variable. So, another label can be marked at this node. Similarly, here we have S4 is equal to 4 into I. So, here the recomputation, we can reuse this computation. 4 and I we have already computed. Here the label is S1, and again we can assign one another label to it, that is S4. Now, next is this is the S5, this is address of B minus 4. So, this is address of B and then minus 4. So, minus will be here, and then the label or the information, that is S5, mean this result will be stored in S5. Now, next we have next statement, that is here S6. S6 is like this, that is S5 and S4. So, this is S5 the array and its index is S4, it will come over here, and this is assigned to S6. So, here we can write S6, and this is the operator that we have. Now, next is to do the multiplication of S3 and S6. So, this is S6 and this is S3, they will be multiplied and result is in S7. So, here we can write S7. Now, next is this product plus S7. So, here we can write another create another leaf for variable product, and then this should be added. So, here we have plus operator. So, plus operator S7 plus this one, and this will be in product, this will be in asset. Now, next statement is asset is equal to a product. So, another information or label or variable name can be added over here, that is product. So, this is product is equal to asset. Till now we have implemented it. Then next statement is S9 is equal to 1 plus I. So, S9 is equal to, this is 1 I plus 1. So, this is 1 I and this is 1, this can be computed, and here plus operation and then S9. Now, this S9 is assigned to 1, S9 is assigned to 1. So, again we can create a label over here, we can simply write I. So, in that way we are we are finding the sub expressions, common sub expressions, and we are using the result directly from the interior node rather than recomputing the sub expressions. Next is if I is less than or equal to 20. So, this is I and this is 20. If it is less than or equal to, then here we will if it is less than or equal to 20, then we will go to 1. So, here we will retain the 1. So, in that way the DAG can be calculated for any 3 address code, and we can find the common sub expressions, and we can easily reduce the tasks of recomputation. So, this is all about this lecture. Thank you.